Right now, Mount Everest is too short. Not too short to kill you. It has done that hundreds of times, and it will do it again this season. Too short for what it is actually trying to be. The crumpled front edge of an entire continent, shoved upward by a collision that has not stopped for 50 million years. So imagine the mountain finally won. You wake up tomorrow and Everest is exactly twice as tall. Before I tell you what happens, I want you to picture it yourself. Really picture it. What do you actually see when you double that mountain? Most people see the same thing: a slightly bigger triangle, more snow, a harder climb, a longer line of people waiting at the summit ridge. That is not what you would get. Because somewhere around the halfway mark, Everest stops being a mountain and becomes something else entirely. Something this planet has never had. Something, as you're about to find out, that it is not allowed to have. And before we go up there, I'm curious where you're starting from. Drop your country in the comments. There's a reason I'm asking, and you'll understand it in about 6 minutes. Let's start with the number. Everest today is 8,848.86 meters. Measured, argued over, and finally agreed on by China and Nepal in 2020. Double it, and you get 17,697 meters. Call it 18 kilometers. That sounds like a bigger mountain. It isn't. It's a different category of object. Your flight into Kathmandu cruises at about 11 kilometers. The summit of a doubled Everest would stand more than 6 kilometers above your window. No pilot would ever fly over it. They would fly around it. Now go higher. Somewhere around 16 to 17 kilometers above the Himalaya sits the tropopause. That's the ceiling on weather itself. Clouds, storms, monsoon, wind above it, the stratosphere. Thin, dry, silent air where nothing ever happens. For much of the year, the top of your doubled Everest would punch straight through that ceiling. Think about what that actually means. The summit would be above the sky. And the jet stream, that river of 200-kilometer-an-hour wind that already rips the famous snow plume off the real Everest, would no longer touch the peak at all. It would wrap around the mountain's waist. You would climb up into a permanent hurricane and then keep going until you came out the other side of it. So could you stand up there? No, and the reason is more disturbing than cold. At the real summit, air pressure is about a third of what it is at sea level. Climbers call everything above 8,000 meters the death zone because your body is dying the entire time you are in it. No amount of rest, food, or acclimatization stops the decline. You are on a clock, and the clock only runs one way. At 18 kilometers, pressure drops to roughly 7% of sea level. 1/13 of the air you are breathing right now. Above about 12 kilometers, breathing pure oxygen through a mask stops working. Not because there isn't enough oxygen in the tank, but because the air outside is too thin to push anything into your blood. Above roughly 15, you need a pressurized suit. The same equipment worn by high-altitude spy-plane pilots and astronauts. And at about 19 kilometers, you reach something called the Armstrong limit. That's the altitude where water boils at your own body temperature. Saliva boils on your tongue. The fluid on the surface of your eyes turns to vapor. A doubled Everest would stop roughly 1 kilometer short of that line. 1 kilometer, that is the entire margin between the tallest mountain on Earth and a place where your body simply evaporates. Nobody would ever climb that in a down suit and an oxygen bottle. The final 5 kilometers would be spaceflight with your feet still on rock. Here's the part that surprises people though. It would not be dramatically colder up there. Air cools as you rise, but only until the tropopause. Then it stops. In the stratosphere, the temperature levels off and eventually starts climbing again because ozone up there absorbs sunlight directly. So the summit might sit somewhere around -60. Brutal, but not fantastically worse than a bad night on the real Everest. Cold is not what would kill you at 18 kilometers. Emptiness is. Now stop looking at the mountain. Look at what the mountain does to everything else. In 1990, the geophysicists Peter Molnar and Philip England published a paper in Nature asking a question that still hasn't fully settled. Do mountains change the climate, or does the climate build the mountains? Chicken or egg? Their argument was that the two are welded together. You cannot lift a slab of crust this size without rerouting the atmosphere above it. The Himalaya already proves that. It blocks the monsoon, wringing the rain out over the southern slopes and leaving Tibet a high, cold desert. It splits the jet stream in two. It is one of the main reasons Asia has the climate it has, and one of the reasons the seasons arrive when they do for roughly a third of the people alive. Now double it. Every one of those effects deepens. The rain shadow behind the range widens and dries. The wall the monsoon slams into rises into the stratosphere. Storm tracks reorganize downstream, across China, across the Pacific, around a single obstacle. One mountain rewriting the weather for half a hemisphere. And this is where your comment comes in. How far away can you see a mountain? That's not geology, that's pure geometry. The The taller the object, the further over the curve of the Earth it can be seen. Today, Everest's summit is theoretically visible from about 335 kilometers away. Double the height, and that number becomes roughly 475. So on a cold, clear, dry winter morning, from the flat plains of North India, hundreds of kilometers from anything resembling a hill, you would look north. And it would be there, a white tooth standing on the horizon of a completely flat country. Haze would usually hide it, but the geometry would allow it, and that is a strange kind of beautiful. So why doesn't it exist? In 1852, a Bengali mathematician named Radhanath Sikdar, working for the Great Trigonometrical Survey of India, finished the calculations on a peak known only as Peak 15. The story goes that he walked into his supervisor's office and announced he had found the highest mountain in the world. But that same survey ran into something it could not explain. An archdeacon and mathematician named John Henry Pratt was checking the survey's plumb lines, weighted strings that hang straight down. Near a mountain range, the sheer mass of rock should tug that string sideways very slightly. Pratt calculated exactly how much the Himalaya should pull. The real deflection was far too small. The mountains were not pulling their weight. Why not? George Airy supplied the answer in the same decade, and it is still the answer today. Mountains float. Crust sits on denser mantle rock the way an iceberg sits in water, and like an iceberg, most of it is underneath. Everest is not resting on the crust. Everest has a root, roughly 40 kilometers of light rock pushed down into the mantle beneath it. That is why Pratt's plumb line barely moved. The extra rock above was cancelled out by a hole of missing density below. Now double the mountain. That root has to double as well. Nearly 90 kilometers of crust driven downward into hotter and hotter mantle, down to where rock stops behaving like rock and starts behaving like very slow liquid. And the mountain still has to hold itself up. The rock at the base of an 18-kilometer column would carry a pressure of around 470 megapascals. Solid granite crushes at roughly 200. So you would not get a mountain, you would get a slump, not a landslide, not a dramatic collapse. The base would spread outward under its own weight like cold honey poured onto a table, and the peak would sink as it went. And even if the rock could somehow take it, the sky wouldn't allow it either. In 1997, Nicholas Brzovic, Douglas Burbank, and Andrew Meigs studied the peaks of the northwestern Himalaya and found something eerie. Across a huge and tectonically chaotic region, the summit elevations clustered tightly around one line, the snowline, the altitude where glaciers form. David Montgomery later gave that idea its name, the glacial buzzsaw. Push a mountain above the snowline and glaciers appear on it. Glaciers grind. The faster the rock rises, the faster the ice takes it away. Past a certain point, the mountain is sawing off its own summit as fast as it can build it. And how fast is that exactly? Everest gains a couple of millimeters a year. Even that fragile gain matters. A 2024 study, with work led by researchers including Matthew Fox at University College London, found that when the Erosion River captured a neighboring drainage tens of thousands of years ago, the sheer weight of rock it carved away let the crust rebound, lifting Everest by a few tens of meters. Tens of meters, that is the scale of the game actually being played here. At a couple of millimeters a year, doubling Everest would take around 4 million years of uninterrupted, undisturbed uplift. No erosion, no collapse, no ice. That has never once happened anywhere on this planet. But it has happened somewhere else. Olympus Mons on Mars is about 22 kilometers high, taller than a doubled Everest. It exists because Mars has weak gravity, no plate tectonics dragging the crust away from the hotspot that fed it, and no rivers or glaciers to cut it back down. Mars built a mountain that big by being dead. Earth cannot, because Earth is alive. Moving plates, running water, falling ice, flowing rock. Every single process that makes this planet habitable is also the process that keeps its mountains small. So look at Everest again. Not as a mountain that could have been taller, as a mountain standing precisely at the ceiling, at the exact point where uplift, gravity, rock strength, and ice all cancel each other out. Push it any higher, and the planet pushes back. Mount Everest is not too short. It is the tallest thing this world will allow.